Okay, hello guys, this is handout 6, acid and bases. In this handout, at first we need to address and actually dive into the questions and try to solve them case by case individually. So the question number one asks, for each of the following Bronsted-Lowry acid-base reactions, first draw the products and label the acid, base, conjugate acid, and conjugate base. And second, use curved arrows to show the movement of electron pairs in the reaction, or provide the mechanism for each reaction. There's one base here that is NH3 or ammonia, and besides ammonia there is water. So in the Bronsted-Lowry acid and base definition, the compound that loses proton or H plus is acid, and the other compound that receives that proton or H plus is the base. So accordingly here, our base is supposed to be ammonia because it's able to receive one of the protons from one of the OH bonds of water here, and actually it's gonna produce the conjugate acid, and after that the conjugate base. So the first we need to address the bond that can individually direct us to release one of the protons, and that special bond is one of the OH that you can see here in water. So as the acid is water, we need to break down one of the bonds, because this is what exactly happens in practice by the aid of the free electron pair of ammonia. So at first we try to write down our arrows like this one to break the bond, and definitely all the 2 electrons in this OH bond are moved directly to the more electronegative atom, that is oxygen here, and we definitely have 1 proton and 1 hydroxide ion. So on the other hand, the free electron pair of ammonia attacks the proton that is just released by water and try to make NH4 plus. That is the conjugate base of this reaction. So we need to address attacking those free pair of electrons from nitrogen in ammonia to the recently released proton from water, like this one. And in conclusion, we have NH4 and the formal charge of nitrogen is plus, because there are actually 4 electrons around nitrogen, and it is 1 less of all the electrons that are supposed to be around nitrogen in the valence shell. The valence shell is supposed to have 5 electrons for nitrogen, and here we have only 4 for nitrogen in NH4 plus. And finally we have the released hydroxide ion here. And one important thing is we need to keep in mind that put all the free electrons around the specific atom after each bond breaking. And also the formal charge for those atoms. So Here our primary base and acids are respectively ammonia, and the compound that is produced by doing the reaction from our base is going to be our conjugate acid, and vice versa. So the compound of the compound of the product that comes out of the reaction over the acid is going to be our conjugate base, that is hydroxide ion here. Next example, again we have nitrogen in this aromatic kind of compound, and on the other hand we have HCl. So there are a lot of electrons or three free electron pairs around chlorine in HCl, and on the other hand we have one free electron pair around nitrogen. So the best candidate to be an acid regarding the electronegativity between the atom pairs in both of those compounds is going to be HCl, and so we need to break this bond and release the proton inside this compound. So we have, just like the previous one, this arrow that comes to the more electronegative atom, that is chlorine here, respect to hydrogen, and then we are able to release the hydrogen as our proton or acidic proton. So this one plays the role of our acid, and this one is going to be our base. Why? Because the free electron pair of nitrogen will attack to the proton that is recently released from our HCl. So we have the larger arrow like this. And finally we have our conjugate acid as the product of this reaction regarding our base change, that is almost the same compound, except it is an ion instead of a neutral compound. So the structure will be this structure. As you see here, the only change is we need to add one extra nitrogen-hydrogen bond to the other bonds here for our nitrogen atom in this compound. So we have and this one is the same CH3 or methyl group that we already had here. And keep in mind to put the formal charge for nitrogen, because it already has 4 bonds instead of 3 bonds, and all the electrons around that, the electron number around that is in the valence shell, is 4 instead of 5, so it's going to be plus nitrogen with the formal charge, that is plus. And then we have the product as a conclusion of breaking this bond, and that's going to be our chlorine ion. And our chlorine ion will have 8 electrons at the valence shell instead of 7. So it's gonna have minus as the formal charge, or Cl minus as the ion. So regarding the reaction, we need to have the transformation of our base as the conjugate acid. So this compound will be our conjugate acid. And this compound is our conjugate base. Our conjugate base is the transformation of our primary or reactant acid as the product that you can see right here. Number C is 1-hydroxylic acid. That is definitely an acid here. And another compound, that's going to be our base. Because comparing to hydroxylic acid, it cannot be another acid or something like that. So it is definitely a base that incorporates into this reaction. So first we need to go over the OH bond of the acid and break the bond and release 1 proton. The same thing that we did for former ones. So we break the bond and release the proton. And regarding the free electron pairs around oxygen, 1 free electron pair must attack to the proton. So the result will be our carboxylic ion. And also phenol is another product here. You can see we have 1 OH. That is an alcohol functional group. Stick to one of the carbons in this aromatic ring. So the first one is our conjugate base, just like the other ones. Why? Because it directly comes out of our reactant acid. And the other one is our conjugate acid. That is the transformation from our primary or reactant base. And keep in mind that if you want to run this process or the reaction on the other way around, from the opposite side, we can talk about the reverse kind of reaction. For example, we can break the bond of OH here and release this proton, and then attack the free pair of electrons from this oxygen from the conjugate base, that is carboxylic ion, to the released proton, and have this conjugate base and acids correspondingly at the left side that you can see right now. Okay, number 2, ask us to compare the protons indicated in the following compounds and say which protons is more or most acidic. Begin by drawing the conjugate bases and then compare them. So in order to in order to show the conjugate bases regarding the two different protons, at first we need to draw the structure of them. So if we assume that this proton is number 1 and the other proton is number 2, to have a conjugate base regarding releasing the proton number 1, we have this molecule or this ion. And regarding releasing the other proton, that is proton number 2, from this side of the compound, we have this new ion. Okay, if we want to choose one of the two produced conjugate bases, we need to pay attention that the most justified one, regarding the rules that we've already had about having the major and minor products of the resonance processes and applications that we've done so far. Right here, we see that the negative charge is over carbon, while the negative charge at the right side or at the right one is on nitrogen. So as nitrogen is a more electronegative atom respect to carbon, this one is more stable, and so this is more acidic. I mean, the proton, the released proton from this ion will be more acidic. So that's why number 2 is more acidic than number 1 as the released protons. We move forward to the other one. That's going to be this molecule. So we have 3 different protons that are actually effective in determining the acidity of this compound totally. So this is proton number 1, proton number 2, and proton number 3. Just like the former one, we need to produce different conjugate bases regarding releasing those different 3 protons from the primary compound. For this one, we have this ion with a negative formal charge over oxygen. And the rest of the compound is going to be as it was before. For the second conjugate base, we want to release the second proton. So we have HO, this proton will be released, so we have a released free pair of electrons over this carbon with a negative charge for that, and the rest of the compound will remain as it was before. And finally, the last and the third conjugate base will be this one. Okay. To find the most acidic one, we need to consider all of these three conjugate bases and see which one will be more stable or which one has more basic power or more basicity, because the one with the most basicity is the one that's gonna be related to the most acidic proton. So in number one, we have negative charge over oxygen. In number two, we have it over carbon. And in number three, we have it over this oxygen. So our candidates are number one and number three, because both of them have negative charge over the more electronegative atom, that is oxygen here. The difference between number one and number three is, in addition to having a negative charge over oxygen, we have one double bond that is a neighbor to the oxygen for the first conjugate base. So it tells us that this proton that's going to be released from this oxygen and give us the first conjugate base will be more acidic because of the double bond as a neighbor of this oxygen, while there's no double bond as a neighbor for this one, so this is more acidic. The other thing that we can mention about the acidity of this proton respect to the third proton is keeping in mind that sp2 bonds essentially have more electronegativity than sp3 bonds. So this carbon that is the neighbor of oxygen here, the neighbor of the oxygen for proton number one, has more electronegativity than this carbon that is the neighbor of the oxygen connected to the proton number three. So that's going to be a good reason to say this proton is more acidic than the third proton. So for the next question, as you can see here, we want to break the bonds of CH, break the CH bonds that all are non-polar from the carbons that you can see and indicated in this carbons number 1, 2, and 4. So for the conjugate base number 1, if we want to release the proton from the first carbon, if we can name them from left to right, so this naming is not for nomenclature, it's just to indicating the process. The nomenclature definitely starts from right to left because of the rules, and from the right our carbons actually have some shortest branches rather than the left side. So we have 1, 2, and 3 just to show the conjugate bases that we'll have in the production as running the reaction, or the product of breaking the CH bonds from this side. For the first conjugate base, we have this compound For number 1, we have a negative carbon, 1 free pair of electron, and 1 formal charge of a minus or 1 negative charge over the carbon, and everything else is the same for the other carbons. For the conjugate base number 2, we do the same kind of process over carbon number 2 here. So we have this compound. And for the third one, we try to break the bond of the third carbon. Number 1, carbon number 2, and this is carbon number 3. So for finding the most acidic hydrogen or proton from among these 3 products, we need to find the most electronegative state for each of those 3 conjugate bases. So regarding this logic, the most acidic is going to be placed between the highest electronegative atoms that are fluorine atoms. So number 3 is actually placed among all of the fluorine atoms that you can see right here, and it says the proton or the carbon that is here, carbon number 3, has the most electronegativity respect to the other carbons that are carbons number 1 and 2. So this is the most acidic proton that will be released from the primary compound, and also the most acidic proton is here at carbon number 3. For the third question, it says the base reacts on the most acidic proton in the following compound. It asks at first draw the conjugate base for the given Bronsted-Lowry acid-base reaction, and then use curved arrows to show the movement of electron pairs in the reaction. Okay, the first thing we need to do for this question is finding the most acidic proton, the left compound, and then try to react it with the hydroxide ion and make the conjugate base and acids at the right side. So there are different OH groups at the left compound, as you can see right here, together with one carboxylic group that's here, and one ester group, as you can see right here. So the pKa of the carboxylic acid is the lowest pKa from among the other functional groups like alcohols and ester. And a accordingly, this part or the proton of the carboxylic group is going to be the most acidic proton. So this is the best candidate to incorporate into the acid and base reaction, and it gives us the conjugate base. That's going to be the new compound. So we can say that every part of the big side of this compound will be, for example, R. This is just for indication. And then we have R, the carboxylic ion, and water that you can see right here. So this is our acid, and the first product here is our conjugate base. And so the hydroxide is our base, hydroxide ion is our base, and water is our conjugate acid. And when we want to use the arrows, we need to break this bond and locate all the 2 electrons of the OH bond only to oxygen, because oxygen is more electronegative than hydrogen, and then attack the free electron pairs of the hydroxide ion to that released hydrogen, like this. For the question number 4, it asks about different reactions or different Lewis acid-base reactions, and asked us to use curved arrows to show the movement of electron pairs in the reactions, and then label the Lewis acid base and draw the structure of the products. So in Lewis acid-base reactions, we need to have one free electron pair that's going to be donated by one of the compounds or one of the reactants, and an empty space that's going to be an empty orbital from the other partner of the reaction or from the other reactants, and move the whole free electron pair from the donor to the receiver. So here, if you can see in aluminum, there are only 3 electrons in the valence shell, and it's most talented to be the full octet. So the Lewis acid and base reaction in this case will be using one of the free electron pairs of beryllium here, bromide here, and put them in the free orbital around aluminum. That free orbital will be the valence orbital for that. So we'll have this free electron pair from bromide to aluminum. So the receiver of the free electron pair will be our Lewis acid, and the donor will be our Lewis base. And finally, we have this structure for our product. this is the new bond that the Lewis acid and base reaction built for us. So bromine shared one of the free electron pairs for the bond between itself and aluminum. That's why bromine will have a plus or positive formal charge, and aluminum has a negative formal charge here, because right now there are four electrons at the valence shell of aluminum. For the other one, or for number B, we need to do the same process. So at first we need to find the free electron pair or the donor of them, and the atom of one of the reactants that's going to be the receiver for that free electron pair. So while the first reactant here has a double bond, we can at first apply the resonance rules over this to transform this compound to something different, and then we can apply the Lewis acid-base reaction and process over that. So we can apply our resonance rules and have the arrow to build this structure, the resonance structure. So keep in mind, when we move this one of the double bonds to oxygen here, our carbon will have only three bonds, and that's why it's going to be carbon plus. And accordingly, we have the negative charge over our oxygen. Now we use the same reactant as we had before. Now we have an atom in one of the reactants that is fully ready to accept a free electron pair, and that's going to be our carbon plus, and the free electron pair will be the free pair over our nitrogen in the second reactant. So we have this arrow in our process, and accordingly the first reactant will be our Lewis acid, because it receives the free electron pair, and the other one is our Lewis base because of donating the free electron pair. And finally we have such a compound. At the same time, because nitrogen will have four different bonds, because it donates the free electron pair, and to make the four bonds, it's going to be a positive nitrogen with a positive charge over that. And the other connection is the bonding with two methyl group. CH2 and CH3. So if you look at the reactants, you don't see any negative or positive charge over either of those compounds, but at the right side we have a compositional compound as our product with one plus and one minus charge. So it means that in total all the charges that we have over this final product will be zero, and that's the same for the total charge of all the reactants at the left side of this reaction. Okay, this was our acid and base workshop, and I hope that it could be helpful. Thank you for your time and patience.